Good day. Today we are going to discuss a simple introduction of dynamics of rigid bodies. So to begin, we have learned from physics that mechanics deals with the study of forces. And these forces are applied to objects that are either at rest or stationary, or those that are in motion or already moving. We can see that under mechanics we have two branches. We have statics, which deals with forces acting on objects at rest, and dynamics, which deals with the study of forces in their motion. So under dynamics, there are also other sub-branches. We have kinematics and kinetics. And in our subjects, this will now be our main interest. So what are we going to learn in CE 2221? So we're going to learn dimensions, units, and error estimations, and the difference between kinematics and kinetics of particles of rigid bodies. So a summary of the topics that we are going to learn in this unit will include translation and rotation of bodies that are subjected to forces and torques, work, energy and power, free and damp vibrations, gear trains, belts, and belt drives, and the application of translation and rotation of bodies to real engineering problems. So as you can see, dynamics would now be a more complex topic than your physics and static subjects. So what is dynamics? Dynamics is a branch of mechanics that would deal with the motion of bodies that are under the action of a force. The foundation of our analysis for this unit would include forces and torques, vibrating systems, simple mechanisms, gears, and belt drive. So as we have said, dynamics can be divided into kinematics and kinetics. So what is the difference between the two? Kinetic or kinematics is the study of the geometry of motion and would now relate to the displacement, velocity, acceleration, and the time of motion without regards of the cause, which is the force. While for kinetics, this is now the study of relations existing between forces, mass, and motion of a body. This is used to predict motion that is caused by a given force. Likewise, kinetics can be used to predict or determine the force that is required to produce motion. In kinematics, there's absolute motion and relative motion. Absolute motion is the motion described with respect to a reference frame or a coordinate system. And relative motion is the motion that is described with respect to a moving coordinate system. So as we have defined or discussed from your physics, there are different types of motion. And for dynamics, we'll be discussing translational motion. And under this, there are two types, which we call the rectilinear motion, which is the motion of a particle along a straight line. The other type of translational motion is the curvilinear motion, in which a particle moves along a curved line in either 2 or 3 dimensions. So, for rectilinear motion, as we have defined, particles will now be moving along a straight line or in one dimension. And for any kind of motion, we define the motion with its position, which is either the positive or negative distance from a fixed origin on the line or a fixed reference point. So in our diagram, we have point O as our point of origin or our reference point, and the particle has moved to point P. Thus, the distance between point O and point P is our position x. So in our example, the position now is equivalent to 5 meters. And it is a positive distance as it is to the right of our origin. So the motion of a particle can be expressed as a function of time, or that is defined using graphs, such as your position versus time graph. So as you can see in the graph, from the figure, we could simply identify our values, such as their position in terms of time, and as well our velocity. So the motion of particle can be identified if the position coordinate is also known for all the values of t. So another way to define the motion of a particle is through its velocity, which is defined as the rate of change in position of the particle. The velocity now can be computed as its average velocity, which is simply the change in position divided by the change in time, or its instantaneous velocity, which is the limit of the change in x with respect to time as the change of time approaches zero. So our velocity now may be a positive or negative value depending on its position. So the particle's speed is simply the magnitude of our velocity. So in our figure, we have point O as our reference point. So at a certain time t, it has an equivalent distance of x. And from point P to P prime, there is also a change in position, which is delta x. And the time now to travel P to P will be your delta t. Okay? So in total, the time now to travel from your reference point to the new position P prime is t plus delta t. So if I want to take now the velocity of the particle from point O to P, that will simply be x divided by time, or if I want to take the velocity of the particle in traveling from point P to P prime, that would simply be delta x divided by delta t. Likewise, it would be the same if I will want to determine the velocity of the particle at prime P from point O, that will simply be x plus delta x all over time plus delta time. So if the particle now is moving to the positive x direction, or the velocity is greater than 0, then it is a positive velocity. And if the particle is moving in the x direction, in which the velocity is less than 0, then it is a negative velocity. Another definition of the motion of a particle is through its acceleration, which is simply the rate of change in velocity. Same as for velocity, the acceleration can be defined by its average acceleration, which is simply the change in velocity divided by the change in time. Likewise, we also have the instantaneous acceleration, which is simply the limit of the average velocity as delta t reaches 0. Take note that we have a positive instantaneous acceleration when the velocity is a positive value and is increasing, or we have a decreasing negative velocity. In contrast to this, a negative instantaneous acceleration will happen if we have a decreasing positive velocity or an increasing negative velocity. So the motion of a particle can be determined if the position is known for all the values of time. The conditions of motion are specified by the type of acceleration that is experienced by the particle. And from this acceleration, we can now determine the velocity and position through two successive integrations. Three classes of motion may be defined through acceleration as a function of time, or as a function of the position, or a function of the velocity. So to understand the relationships of the acceleration, time, position, and velocity, let us take this into consideration. So let's have our functions of the acceleration as time, acceleration as a function of position, and acceleration as a function of velocity. So the kinematic relationship now for acceleration as a function of time is given by the equation dv all over dt equal to at, or that is the derivative of velocity with respect to time is equal to acceleration as a function of time. For position, that can be written now as v dv with respect to x is equal to a of x. And for velocity, it can be defined by the two equations dv all over dt is equal to acceleration as a function of velocity, or v dv dx is equal to a of v. So to solve now for our values, we can now apply our integration. So if we integrate now from your calculus, so transposing dt to the other side, we can rewrite the equation as the integral of dv from vo to any value of v is equal to the integral of a as a function of time dt from 0 to time. Likewise, for position, that will simply be the integral of v dv from vo to v is equal to a as a function of x dx from xo to x. And we have for velocity the integral of dv divided by av from vo to v is equal to the integral of dt from 0 to t. And lastly, we have v dv divided by a of v is equal to the integral of dx from 0 to x. So as a summary, in finding the velocity or the displacement, this would now require integration of the acceleration equation. And for the acceleration, this can now be solved through the derivatives of your velocity or displacement. So if we are going to observe or recall from your physics, we have learned that the acceleration is simply the second derivative of the position, and velocity is its first derivative. So again, from our equations of displacement or position, velocity, and acceleration, we have observed that there are no value of forces that is required in solving for our motion.